Okay, so this next part is asking us the probability that the person is an adult or disliked the ride. Now, when you see or, that is a union. That means that you're putting those two groups together. So you want to include all the people who are adults, which that's all of these guys, and you also want to include if they disliked the ride. Well, everybody that disliked the ride was these guys. So you want all of these, but you just don't want to double count anyone. Okay, so you don't want to count the 30 twice. Okay, so you're just going to add 17, 30, and 28. And that will be out of your total of 130. Okay, so if you add all that up, let's see, what do we got here? We got 58 and 17. Okay, so we have 75 out of 130, and you can reduce that if you want, or you can use a decimal approximation. Okay. The next part is what's called a conditional probability. It says, what's the probability that they liked the ride given that he or she is a child? This word here, the given that, is what tells you you have a conditional probability. Now, we have a formula for that, but when you're talking about a table, you really can just use logic to find your way through this. So when it says, given that he or she is a child, that means you are only talking about the kids. So I'm just going to highlight these kids right here. These are the only ones we're talking about now. That is our entire new group. Okay, so we have 72 kids. That becomes our new group. So out of those, they want to know how many liked the ride. Okay, not how many liked the ride out of everybody, just out of those. So there were 55 that liked the ride out of 72 children. Okay, so we can just use logic for there. Okay, the last one we have another conditional probability because I say give. It says given that. So the probability that they're an adult, given that he or she disliked the ride. Okay, so I kind of need to change things around here. I don't want to just look at the kids anymore. I'm afraid I'm getting my paper's a little messy there, but our new group is just those that disliked the ride. So you want to just look at the second row. Okay, my colors are failing me a little bit here. So your new total is just this 47, the ones that disliked the ride. And out of those 47, there were 30 adults. Okay, and that's approximately 0.638. Okay, and now we're going to have just a few simple examples here. These are going to be for OR events. Okay, we know the OR is a union. You're putting the two groups together. Okay, so for this one it says if you select a card at random from a standard deck of cards, what is the probability of choosing a king or a club? Okay, and what you want to do here is make sure that you don't double count. So I'm going to represent this with a Venn diagram. You have your kings and you have your clubs. So you need to take a minute and think, well, how many are in both categories? Well, there is one king that is a club. Okay, and so there is one in the overlap, and you want to avoid counting that twice. Okay, so when you think about how many clubs there are, there's 13 cards in a particular suit, so there would be a total of 13 here, so that would be 12 and 1. When you think about how many kings are in a deck, there's 4 different suits. There should be a total of 4 in this circle, so we'd have 3 and 1. Okay, so when they say the probability of choosing a king or a club, a couple ways you can look at that. We want or, so we want the union of this. Okay, we could also put how many cards are left that aren't in either of those categories, but I'm not going to need the information for this problem. Okay, so the or means the union. Put this together. Okay, and so we know that there are 52 cards in a deck. And we know that we have 4 and 12. We are using 16 of them. Okay, so you could reduce this. Okay. Another thing I want to do is show you how that corresponds with your formula. So the probability of A or B, which is the same as A union B, is the probability of A, which if we did, in this case, we're really talking about clubs and kings. Okay, so we could just say that was the probability of clubs, which is 13 out of 52, plus the probability of kings, which is 4 out of 52. But then you want to subtract what's in the overlap because we counted that guy twice, minus 1 over 52. And you come out with the same thing we did before. Okay, but this just kind of illustrates our property there with our formula for unions. Okay, so here's another example. If you select a card at random from a standard deck of cards, what is the probability of choosing a red card or a queen? So the or again means union. You're putting them together. So without a Venn diagram, I can say, hey, for red cards, that's going to be 26 out of 52. And I'm going to put that together with all my queens, so that's 4 out of 52. But you want to take off anything that's in the overlap. So you want to think to yourself, how many red queens are there? Okay, and there's 2, so you're going to take that off. And so you get 28, 30 minus 2. So 28 over 52, and again, you can reduce that if you want to. Okay, here we have another example. A bag has 20 coins numbered from 1 to 20. A coin is drawn at random, and its number is noted. What is the probability that the coin drawn has a number that is divisible by 3 or by 5? Okay, so what you want to do here is just write out the numbers that would be divisible by 3. So we just have 3, 6, 9, 12, 15, and 18. Okay, we only want to go up to 20. Those are divisible by 3, divisible by 5, so we would have 5, 10, 15, and 20. Okay, now notice that we do have 1 that repeats here. Okay, so if you want to count, we know it's going to be out of 20. So you could either just count these but don't count this twice. You could just go 1, 2, 3, 4, 5, 6, 7, 8, 9. And you know it's 9 out of 20. Or you can do the probability that it's a multiple of 3, which is 1, 2, 3, 4, 5, 6 out of 20, plus the probability that it's divisible by 5, which is 4 out of 20, and you can take out the probability that it's in both of them, which would be 1 out of 20. So there you would have 9 out of 20. Okay, we're going to do a couple of these that are AND events. Okay, so you see you choose 2 cards from a standard deck of cards, but you do replace the card. Okay, so that's important. So you have just as good a chance of getting a probability of a certain card the second time you do it as the first time you do it. Okay, so it says you do replace the first card before choosing the second. What is the probability of choosing a spade and a heart? Okay, so your probability of choosing a spade is 13 out of 52. There's 13 spades. Okay, if you put it back in, then you've got the same, all the cards are back in the deck. Your chances of getting a heart are 13 out of 52 again. So you can just say 1/4 times 1/4, which is 1/16. Okay, in that particular case was an example of 2 independent events. Those were completely independent because what I did in the first round did not affect anything in the second round. So if you have independent events, then the probability of 2 things happening, you just multiply the probability of the first one happening times the probability of the second one happening. And if you'll remember that I showed you that formula is on your formula sheet for independent events. Okay, dependent events are a little bit different. Okay, it says you choose 2 cards from a standard deck of cards, but do not replace the first card before choosing the second. What is the probability of choosing a spade and a heart? Well, for the first one, your probability of choosing a spade is 13 out of 52. But then that card is pulled out, it is not replaced. Okay, so now there are only 51 cards in the deck. So when you go to choose a heart, there are still 13 hearts in there because you assume that you had success on the first time. You assume that you got out a spade. Okay, and so there are still 13 hearts in there, so you would be 13 out of only 51 cards now in the deck. Okay, so that's equal to, when you reduce that, 13 over 204. So what you see for dependent events of the probability of A and B happening, a spade and then also a heart. Okay, so for the probability of A and B happening if it's dependent, here the notation you have is the probability of A happening, that was probability that I got a spade, times the probability of B given A. So remember this little guy right here means given. So that's the probability of B happening given that A already happened. So we just said we were already successful in A. Now, given that that happened, what's the probability of B? So given that I took the spade out, what would be the probability of now getting a heart? And we multiplied times that. Okay. So here, for example, we have if a coin and a die are tossed at the same time, what is the probability of receiving heads and a 6? Okay, so these are independent. When I toss a coin and roll a die, these have nothing to do with each other. Okay, so if I toss a coin, my chance of getting a heads is 1 out of 2. My chance on that die of getting a 6 is 1 out of 6. So that probability would be 1 out of 12. The next one says, what is the probability that 2 children in a family are both girls? Well, when you go to have a kid, you got a 1 out of 2 chance of having a girl. You have exactly the same chance. The fact that you had one girl does not diminish your chances of having another one. Thank goodness. And so then we multiply by 1/2 again, and you get 1/4. So those are 2 examples of independent events. Okay. Here we're going to shake it up a little bit. We have a box that contains 4 red and 2 yellow tickets. 2 tickets are randomly selected from the box, one by one, without replacement. Pay really close attention to those words. Okay, so once we take one out, we're not putting it back in, so this is now a dependent event. Find the probability that both are red. Well, if you think about this, you have 4 red and 2 yellow to start with. Okay, so your probability of getting a red is 4 out of 6. But now, since you took that out, there's only 3 reds. So your probability of getting a red the next time is 3 out of your total of 5. Okay, so we can reduce that, and we would have, we can reduce a little more. Okay, and we get 2/5. Okay, the next one, we're going to start with the same deal. We're going to start with 4 red and 2 yellow tickets. They want the probability that the first one's red and the second one's yellow. So on the first one, probability that it's red is 4 out of 6. And I know I can reduce things here. I don't tend to because it makes more sense logically as I'm taking them out to take 1 off of the denominator each time a ticket is pulled out. Okay, so the probability now, the first one's red, so now there's only 3 red. Okay, so the probability that the second one's yellow, there's 2 out of a total of 5. Okay, and if you multiply that, you'll get 4/15. And the last one here, it says a hat contains tickets with the numbers 1, 2, 3, all the way up through 20 printed on them. If 3 tickets are drawn from the hat without replacement, okay, so we're dependent again, determine the probability that all are prime numbers. So we need to list out all our prime numbers. 1 is not defined to be prime. Okay, a prime number is a number larger than 1 whose only factors are 1 and itself. Okay, so I'm going to list out my prime numbers, and those are 2, 3, 5, 7, 11, 13, 17, and 19. There are, in fact, 8 prime numbers in this interval. Okay, so my chance of getting a prime number the first time is 8 out of 20. But I'm going to assume that I was successful. I got a prime number. So there's now only 19 total tickets, and I took one of the prime numbers out. So there's only 7 left. And then again, on the last one, there are only 18, and I took one of the primes out again, so times 6. And this is approximately 0.04